In this video, we're going to take the mesh rectangle from the last video and we're going to set it up and solve it using boundary conditions that we have from the initial problem. And to do this, we're going to start with setup. Just double click that. Most of these you can leave the same. If you click this, it'll change it from a 32 to a 64-bit floating number. So increasing the processing power, but also the precision of the answer. Since it's a simple problem, we aren't too worried about processing power, so we go ahead and increase the precision that we use. So the setup window is going to take the mesh that you already have and automatically pull it in. Now, the first thing you want to do is just click check here, and that'll make sure that there are no big problems with your mesh. So that's important before you get too far in the problem, especially with more complicated models. Next, you get scale and just make sure that your entire model is within the scale. So you have 0 to 3 meters in the x direction, 0 to 0.1 in the y direction. So that's good to go. One last thing you can do to make sure to upload everything correctly is to click all these and unselect them, and then one at a time display them and make sure that what's popping up is what you think should pop up. So everything's good to go there. Under the solver for this, we're just going to leave the type under pressure based. One thing we're going to change is for planar to axisymmetric, like we talked about to now. Instead of using x and y coordinates, it's going to talk about them as axial and radial coordinates. Next, you go on to models. A lot of good tools here, especially in Arrow 2, you talk about the different turbulent models here, the different equations they use, so you can select which model you want to use. For this problem, we're just going to keep it on laminar. Down to materials. We create a new material to match the problem. So we'll just call it sample fluid. Set this as 1, and this is 2e to negative 3. And then to make sure that it's being used, go down to cell zone conditions, double click on the zone, and the material name is the example fluid. Next, we'll set the boundary conditions. So you start the inlet. It's already type under velocity inlet, so that's correct. Under edit, we'll change components. And now you can see that it gives us options to change the gauge pressure, axial, and radial velocity. So we'll keep gauge pressure at 0 so that it just uses the atmospheric pressure. And we'll set axial velocity to 1 meter per second and leave radial at 0. Now just to double check that the atmospheric pressure is set correctly, hit operating conditions, and you can see that this is the atmospheric pressure, which is correct under 1000 pascals. Next, check the outlet, pressure outlet, edit, and gauge pressure is 0, so that's correct. The top is a wall, so you just want to make sure that the no slip boundary condition is set for that wall. And then the axis is set as an axis. So that is all correct. The boundary conditions are good to go, and you can continue moving on with the model. So next, you can go down to solution methods. We'll leave these here for now, and we'll talk about these more in later videos because they are important for more complicated models. We can go to monitors and edit the residual monitor. Right here under equations, you can set the absolute criteria for the residuals, and essentially by editing this, by making this a smaller number, you're increasing how long it's going to take to process, but you're increasing the precision of the answer. And since it's a simple problem, we can get away with setting this to 1e to negative 6. And then we'll initialize our problem. So hit standard initialization and 1 meter per second the axial velocity. And this just gives the the processor a place to start the calculation and hit initialize. Now before running calculation, we'll set up a graphic. So I hit graphics, double click contours, contours of velocity, axial velocity, filled, and display. And so to zoom in, click and hold the scroll button and make a box from left to right. Hit draw mesh, display, close. Now the reason I do this is just to show you that what's happening here is these top nodes are all at 0 meters per second initially because of the no slip boundary condition, and every other node out here is at 1 meter per second because of the initialization that you just set. And so all the computer is doing is averaging between 0 and 1 right here. So that should make sense, based on what you know of CFD. So we'll start off, we'll run iterations. We'll just run 10 to calculate. And these are the residuals. So you can see that as you start to iterate, the residuals become smaller and smaller. And to see what that does, you can go back to graphics, your contour, display, and you see this looks a lot different now. And by hitting this button, you can see the whole tube. So if you just look at the middle now, that the velocity is more spread out, a lot more spread out than it just was. So close that, and now I'll increase iterations to 1,000. Now it's not really going to do 1,000 iterations, it's just going to iterate until it reaches the residual value that we set earlier, which is 1 e to the negative 6. So you can see that it was waiting for this value to get that low and then stop calculating. Go to your graphics again, contours, display, and now you can see more of what you'd expect from this type of problem. And in the next video, we'll go ahead and use the post processor to see what we can do with these results.